Hello all, welcome to this new lecture. In this lecture, we will discuss JPEG Standard. JPEG Standard for image compression. So JPEG stands for Joint Photographic Experts Group. So this JPEG Standard is given by this group. So its name, its abbreviation is JPEG. Now in JPEG, we achieve image compression in three steps. Which are these three steps? DCT computation, quantization, and variable length coding. So first, what do? We take the DCT transform of the original image. We quantize those coefficients, and then we do the variable length coding on the quantized coefficients. So here, if we look at the block diagram of JPEG encoder, so here we have an image. So in this diagram, three planes are shown because it may be representing a color image. So we will consider only one plane. So first of all, what is done? This plane, this image plane, will be divided into 8 cross 8 blocks. That means it is divided into 8 cross 8 sub images. So this will have 8 rows and 8 columns. Similarly, this will also have 8 rows and 8 columns. This way, it will be divided into 8 cross 8 sub images. Now each sub image is taken and this sub image is first scaled. How it is scaled? Each coefficient of this 8 cross 8 block will be subtracted by 2 raised to the power n minus 1, where 2 raised to the power n is maximum number of gray levels. So in gray image, the maximum level of gray level is 2 raised to the power 8, that is 256. So 2 raised to the power n minus 1, that is 7, that will be equal to 128. So from all the coefficients, 128 will be subtracted. Now from those coefficients, on those coefficients, we perform DCT. So 2D DCT will be performed on these coefficients. So after that, we will get the DCT coefficients over here. Then the DCT coefficients are quantized. So in quantization, what do? Here, a predefined quantization table is used. So these coefficients are divided by the quantization table, and then the resultant coefficients are truncated or rounded off to the nearest integer. And after that, we get this f hat uv, that is the output of quantization. So this output then is zigzag coded. Zigzag coded means this uh, 2D array, that is 8 cross 8 2D array, will be converted into a 1D array. How? How do we do the zigzag coding? So suppose this is our 8 cross 8 2D array. So we will convert it into 1D array. So we will not write 1D array like this. First these 8 elements, then these 8 elements, then these 8 elements. So to convert this into 1D array, what do? We do the zigzag coding. So first we will write this coefficient, then this coefficient, then this, then this coefficient, and this way here we will come, then here this way we will go, and like this in zigzag fashion we will encode them. So this will be the first element, and this will be the last element, and this will be the sequence of the elements in the 1D array. So this is called zigzag coding. So the reason of choosing zigzag coding is because this coefficient is representing the least frequency or the zero frequency coefficient, that is DC coefficient, and these coefficients are low frequency coefficients, and these coefficients are high frequency coefficients of the image. So these coefficients, this 1D array we want in the order of increasing frequency. So that is why we have coded it in the zigzag fashion. We will discuss it later in the detail. Now after zigzag coding, we separate DC and AC components. So the first component, first element will be the DC element, and remaining elements will be the AC elements of this 1D array, whatever we will get after zigzag coding. So DC coefficient will be encoded using DPCM, differential pulse code modulation, and the AC coefficients are coded using run length coding. And then the entropy coding is done. That means variable length code, Huffman coding is used. So predefined codes will be assigned to these coefficients, DC and AC coefficients, and the coding table for predefined codes we will use here to do the entropy coding. And then output of this will be our compressed image that will be either stored into the memory or that will be transmitted over the channel. So this is simple block diagram of JPEG standard. Now moving forward, these are the outlines of the JPEG standard. So the first step is, first image is subdivided into pixel blocks of size 8 cross 8. So this we have discussed. Sub-image pixels are level shifted by subtracting the quantity to raised to the power n minus 1. So the second step is we level shift the pixels by subtracting each pixel value by 2 raised power n minus 1. Then the 2D discrete cosine transform of the block is then computed and quantized. So after level shifting, whatever 8 cross 8 block we have got, over that we perform discrete cosine transform and we perform the quantization. After quantization, the 8 cross 8 block is then reordered by zigzag coding to form an 1D sequence. So this 8 cross 8 block, this 8 cross 8 array is then reordered. Reordered means we code zigzag in the zigzag fashion and we get 1D sequence out of that. Then a reordered array generated is qualitatively arranged according to increasing spatial frequency. So this we have already discussed that this, since this will be the first element and this will be the order and this will be the last element. So this is uh, generated in the increasing spatial frequency order. That means the first element will be DC coefficient and the last elements will be high frequency elements in the 1D array. Okay. Then the JPEG coding procedure is designed to take advantage of long runs of zeros that normally result from reordering. So after reordering, whatever 1D array we will get, there we will see that more number of zeros will be there in between the AC coefficients, and the high frequency uh, coefficients will corresponding to high frequency coefficients we will get what, mostly the zero values. In particular, non-zero AC coefficients are coded using variable length code that defines the coefficient's value and number of preceding zeros. So AC coefficients are coded using variable length coding, variable length coding, and variable length codes are defined by using what? What is the value of the AC coefficient and how many zeros are preceded the AC coefficient. That means how many zeros have appeared before that AC coefficient. In that fashion, uh, the Huffman codes for the AC coefficients will be defined. Now this we will look in detail when we will take one example. The DC coefficient is difference coded relative to the DC coefficient of the previous subimage. That means for the DC coefficient, we will take the difference from the previous coded subimage and then we will code the DC coefficient. Then we will write variable length code for the DC coefficient. So what will be done? Uh, the DC coefficient of previously coded subimage will be taken and the current subimage DC coefficient is taken, difference is taken, and the difference is coded as the variable length coding, or Huffman code is used for that difference. Okay, so this is the outline of JPEG standard. Now let us understand this by taking one example. So suppose we have taken one sub-image, and on this sub-image we will perform all the operations which are included in the JPEG standard. So suppose these are the pixel values of one 8 cross 8 subimage. One 8 cross 8 block is there. So see here, 8 rows are there and 8 columns are there. 1 2 3 4 5 6 7 and 8. 8 and 1 2 3 4 5 6 7 and 8. 8 cross 8 subimage is there. So let we will understand how this is compressed by using the JPEG. So first one is, since this is the gray image, so the gray levels will range from 0 to 255. That means total 256 gray levels are there. So 2 raised to the power n is 256. So 2 raised to the power n minus 1 will be 128. So it will be level shifted first. So to level shift, the, each element of this subimage will be subtracted by 128. That means 128 will be subtracted from each element of this array. So shifted array, level shifted array is, so from 52, if I subtract 128, I get minus 76. So this is the array which we will get after subtracting 128 from each element. Then the second step is we perform DCT coefficient, DCT transform, discrete cosine transform on these coefficients, on these values. So if we perform DCT operation on previous these coefficients, then we get this array, 8 cross 8 array. So as I told that this is the DC coefficient, that is minus 1 minus 415 is the DC coefficient, and these are the low frequency coefficients, and these are the high frequency coefficients. Now, if we look at this sub-image, then we see that DC coefficient is quite large in magnitude. The lower frequency coefficients are moderate in the magnitude, and the higher frequency coefficients are quite low in the magnitude. That means we can say that the most of the information will be available in DC coefficient and low frequency coefficients of the DCT, of the DCT. So we can truncate the high frequency coefficients from these values. Now next comes is the quantization. So in quantization, what do we do? As we have discussed that in quantization, we normalize these DCT coefficients by using a standard 8 cross 8 array. So this is the quantization table. So this is used to get the to do the quantization. So what is done actually? This whole table, this whole array, 8 cross 8 array, will be divided by this 8 cross 8 array element by element. That means this minus 415 will be divided by 16. Then this 19 minus 19 will be divided by 11. And then whatever fractional values we will get, they will be rounded off to nearest integer. So if we look at the DC coefficient, so this will be, this we will get by this. So t hat 0 0, that will be equal to round t 0 0. So that means this is t 0 0 minus 1415, and z00 is 16. So divided by 16 we get minus 26. So minus 20, and if we round it off, then we will get minus 26. So that will be this one. After dividing minus 19 by 11, we get 2 point something. So that will be rounded up to minus 3. Then minus 62 divided by 10, so that is 6.2, that is rounded off to minus 6. So that way all the values of this DCT coefficients will be divided by these this uh, the quantization table coefficients. So here we can observe one more thing, that the lower frequency coefficients are divided by less magnitude values, and the higher frequency coefficients are divided by higher magnitude values. This is why, because we have discussed that the most of the information will be available in the low frequency and DC components, and very less information will be available in the high frequency components. So by dividing it by the quantization, this table where it will divide the high frequency coefficient by larger magnitude, so it will make more number of zeros in the output array. So we will take advantage of these more number of zeros in the output array. Now this will be zigzag coded. So after quantization, what is the next step? Next step is we zigzag code this array, 8 cross 8 array. So how do we perform the zigzag coding? So first we will write the DC component. So this is minus 26, then this minus 3, then 1, then minus 3, minus 2, minus 6, then 2, minus 4, 1, minus 4, 1, 1, 5, 0, 2, 0, 0, minus 1, 2, 0, 0, 0, 0, 0, minus 1, minus 1, and after this, since all the elements are 0, after this minus 1 all the elements are 0, so we will write end of block EOB element. So this is how this 2D array, the 2D array is converted into a 1D array. Hope this is clear. Now moving ahead, the next step is, after zigzag coding, the next step is how do we code these DC and AC components. So for that, first, what is done? We use three tables to code these DC and AC components or coefficients. So what is done is, first we need to find the category of each element. That means if our coefficient is 0, then its DC category is 0, and there is no category in the AC coefficients for 0. If it is from minus 1 to 1, then its DC category is 1 and AC category is also 1. If it is from minus 3 to minus 2 and 2 to 3, then its category is 2 and AC category is also 2. If it is minus 7 to minus 4 and 4 to 7, then its category is 3 and AC category is also 3. Similarly, if it is minus 127 to minus 64 and 64 to 127, then its DC category is 7 and AC category is also 7. That way, this is defined for this much large values in the negative and positive. So minus 32,767 to minus 16,384 and 384 to 32,767. If the coefficient falls in this range, then its DC category is F, and for this there is no AC category, and for this range it is this. So this is how we define the category for each DC coefficient and AC coefficient. Okay. After getting the category of DC and AC coefficients, what do we do? Based on the category, based on the category, since here we have total 0 to F categories for DC code. So here 0 to B are given, 0 to B categories are given. This, so for this we have base code, base code, and length of the code. So that is given. So this table also we will use to code the DC coefficients of the uh, quantized or that 1D array we have got after the zigzag coding. How we will use this table, that we will understand while doing the coding for these coefficients like minus 26, minus 3, 1. So And the second is the AC coefficients. How AC coefficients are coded? So here AC coefficients are coded this way. So first we find the run and category. So category we have got from this range, in which range the AC coefficient is falling. From there we will get the category. And how do we find the run? How many number of zeros are preceded by that number, by that AC coefficient? That is given by run. If there is no zero before that AC coefficient, then that run is zero. So the run is zero for that. If the one zero is preceded that AC coefficient, then run is 1. So on, this table is extended till F run and A category, till F run and A number of categories. So I have taken a part of this table. So if you want to check out the full table, then you can refer this book. In this book, this whole table is given. So first 0 0, this is code, base code for end of block. This end of block we have discussed. So when all the remaining uh, numbers are 0, then we use end of block. So if end of block appears, then we use this 10104. If AC coefficient is 1 and there is no 0 before this, then we use this code, this base code. Then same way we find the run and category for each AC coefficient, and that base code corresponding to that we will use the base code for the AC coefficient. Hope this is clear. Now let's understand how we code this, how the entropy coding is done for this 1D array. So first let us code this minus 26 DC coefficient. So let's understand this. Is the DC coefficient of, of its immediate left was minus 17, and the resulting DPCM difference is, now since we have discussed that DC coding is done using DPCM, differential pulse code modulation. So what is done in this? The DC coefficient of the current subimage is subtracted. From this, the DC coefficient of previous image is subtracted. So the immediate left image had minus 17 DC coefficient. So first we will find the difference. So minus 26 minus 17, that comes out to be minus 9. So this is our coefficient that needs to be coded, which lies in DC difference category 4. So once we have found this difference, then we will find its category. So the difference is minus 9. So minus 9 falls in this range. Yes or no? Minus 9 falls in this range, and for this the DC difference category is 4. DC difference category is 4. Now we will find what is the base code for this category, category 4. So the base code for DC coding is, this is the category 4. The base code is 101. Base code is 101, and the length of the code is 7. Length of the code is 7. This means what? The base code is 101 and the length of the code is 7. So what we need to do? We need to find the remaining 4 bits of this code, because base code is 101. 3 bits we know, but we need to represent it by using 7 number of bits. So we need to find remaining 4 number of bits. So how do we find the 4 bits? For finding 4 bits, we need to do what? Additional k bits are needed to compute either the KLSBs of positive difference or the KLSBs of negative difference minus 1. So how do we find the KLSBs, k bits? So for that, what do? We represent the difference that will be either positive or negative in the binary form, and the KLSBs of that positive number will be taken, or KLSBs of negative negative binary number -1 will be taken. So let's understand how we will choose these k bits from the difference. So for this particular case, we need to find out four LSBs, because base code we have got 101, we have got, we need to find four LSBs since the code length is 7. So four LSBs we need to find. So four LSBs will be, if the difference is negative, then what we need to do? We need to represent this difference in the binary form. So difference is negative. So -9 is represented by 0 1, sorry, 1 0 1 1 1, right? So -9 is represented by this. Its four LSBs will be 0 1 1 1. Now, if the difference is negative, then we have to subtract 1 from it. We need to subtract 1 from it. So if I subtract 1 from it, what do I get? 0 1 1 1 -1, that will be equal to 0 1 1 0. So this will be used as remaining 4 bits for this code. This code. Now if it was +9, if it was +9, then we will directly represent this 9 into the binary, and LSB 4 bits would have been taken directly. We need not to subtract 1 in that particular case. Now, to compute the DPCM coded DC code word, we get the complete DPCM coded DC code word is 101, that is this base code, and 0110, the four LSBs which we have found by following this method. So let me repeat this method again. So if the difference is positive, if the difference is positive, then you represent the difference in the binary and take the needed k bits from the LSBs of that binary number. If the difference is negative, then you represent that negative into the binary in 2's complement form, take its KLSBs, take its KLSBs and subtract 1 from it. Subtract 1 from it. So in the case of -9, it is represented in binary this way. Its 4 LSBs are taken, and then 1 is subtracted from 4 LSBs. Then we have got the resultant value, that is 0110. So the complete DPCM code will be 101, that is the base code, and 0110, that will be the code which we have found by using this method. Now, how do we find the AC coding? So thus, first non-zero AC coefficient of the ordered array is -3. So how will we code -3? So if we look at P1D array, the next AC coefficient, the first AC coefficient is -3. So to encode AC coefficient, so now in this you see that in the case of AC coefficients, we do not take the difference. We take difference only in the case of DC coefficient, that is the first coefficient. For remaining these coefficients, we will not take the difference from the previous value. We will take -3 as it is. This we will find, for this we will find the AC category. So -3 falls in this range. For this, the AC category is 2. AC category is 2. Now, once we have found the category for the AC coefficient, after that we need to find how many number of zeros are preceded by this AC coefficient. So before minus 3, since there is no zero, so the run value will be 0 for this coefficient. So run value is 0 and category is 2 which we have found from here. So this is in this range. So its category is 2. Since it does not precede any 0, so its run is 0. So that is why we will go to this table. Then we will find its run is 0 and its category is 2. So corresponding to this, the base code is 01. Base code is 01 and its length is 4. Its length is 4. That means from this 01 we need to make a code of 4 bit wide. So here 01 we have got. Now we need to get the remaining two LSBs. So how do we get remaining two LSBs? Minus 3 is there. So we will follow the same procedure whatever we have followed here. So minus 3 will be represented by 100 in binary, right? In 2's complement form, it will be represented by 1. Sorry, the minus 3 will be represented by 0. Sorry. Minus 3 will be represented by 101. I'm sorry. The minus 3 will be represented by 101. So LSB 2 bits we will take from this. So that will be 0, 1. So LSB 2 bits will be 0, 1. So from there we will subtract 1. So if I subtract 1 from 0, 1, I get 0, 0. I get 0, 0. So LSB 2 bits will be 0, 0. Let me reiterate this, restate this. How do we get this? So this 0, 1 we have got from the number of runs and category, and we need to find the LSB 2 bits. So LSB 2 bits will be LSB 2 bits of minus 3 minus 1. So LSB 2 bits of minus 3 will be, so how do we represent minus 3 in binary form? Minus 3 in binary form will be 101. It will be 101. And so minus 2 LSBs of minus 3 will be 01 minus 2, sorry, 2 LSBs of minus 3 will be 01. And since it is negative, so we have to subtract 1 from it. So if I subtract 1 from 01, I get 00. So that is put here. So 00 we have got. So that will be put here. So we have got a 4-bit length code corresponding to minus 3 AC coefficient. So this way, all these all these coefficients will be coded, and in the end, EOB, end of block code word will be put. So end of block code word is 1010. So that is put in the end. Now here, this is our coding, DC and AC coding corresponding to this 1D array, corresponding to this 1D array. So you see minus 26 is represented by 1010110, and then minus 3 is represented by 0100, and then subsequently this way, and last is 1010, that is end of block. Now here this spaces are given only for the readability. We need not to give these spaces while storing in the memory or while transmission. We can directly store this bit stream in the memory. Now, if we look at the number of bits used to represent this 8 cross 8 subimage, that is equal to 92. That comes out to be 92. So the compression ratio will be equal to 512 divided by 92. So how do we get 512? 512 we will get by, since we have this block 8 cross 8, so total number of pixels are 64, 8 cross 8, 64, and each pixel is represented, since it is gray image, so each pixel is represented by 8 bits. So total number of bits will be 64 into 8, that is 512. So 512 number of bits are required, and we have represented it by using only 92 number of bits. So the compression ratio we have got is 5.6. 5.6. So this is how we compress the images by using JPEG standards. Okay, hope you understood JPEG standard. That's it for this lecture. Thank you. We will meet in the next lecture.